Coming up on Destination Tomorrow, NASA looks to the future of flight with a revolutionary airplane design called the Blended Wing Body. We'll also see how NASA engineers intentionally crash aircraft to unlock the secrets of safety. And we meet a retired NASA engineer who helped man achieve supersonic flight at over 4,500 miles per hour. All this and more next on Destination Tomorrow.
Hello everyone, I'm Steele McGonigal.
And I'm Kara O'Brien. Welcome to Destination Tomorrow.
This program will uncover how past, present, and future research is creating today's knowledge to answer the questions and solve the challenges of tomorrow.
Most of us are familiar with crash test experiments on automobiles, which have led to life-saving new car designs. But not many people know that crash testing is done on airplanes as well.
Researchers at the Impact Dynamics Research Facility, or IDRF, at NASA Langley Research Center have been conducting crash test experiments on aircraft for over 25 years. The knowledge gained here has led to drastic improvements in aircraft designs, making flying safer for everyone.
Felicia Dames takes us to the Impact Dynamics Research Facility to find out more. Although most of us don't like to think about it, the thought of crashing creeps into almost every passenger's mind when boarding a plane. We all know that air travel is the safest form of transportation known to man. In fact, statistically, you'd have to fly once every day for more than 8,200 years before you'd be involved in a fatal aircraft accident. But tragically, we know that crashes do occur. Fortunately, NASA operates a unique facility called the Impact Dynamics Research Facility, or IDRF, to research and conduct crash testing of full-scale aircraft. The knowledge learned here is making air travel safer in the unlikely event of an accident. I spoke to Lisa Jones of the NASA Langley Research Center to find out about this one-of-a-kind facility.
Well, 80% of most accidents that occur now are survivable accidents, but we're working to bring that number even higher so that people who are involved in an accident that is classified as survivable walk away. But our main goals have to do with aircraft crashworthiness, testing them and improving them so they're safer to fly in. And the way we test these aircraft is we suspend it from the facility and allow it to swing like a pendulum into different surfaces. And we instrument the aircraft and put crash dummies on, and we collect the data during the test and look at it after the test, along with a lot of high-speed film and a lot of photographic information, and determine if real people will be injured or not. And then we also use the information to change structural things in the aircraft to improve how well it absorbs energy and takes it away from the occupants and prevents them from being injured. So that's basically crashworthiness, preventing the occupants from being injured in a crash. The facility was here already. It was the Lunar Excursion Module Simulator where they trained astronauts to land on the moon. Then in the 70s, there's a lot of aircraft accidents, small general aviation aircraft accidents. And we felt that it was time to do something about it. And so we actually recycled the facility so that we could lift these aircraft and crash test them.
The IDRF team set out to discover why crashes that should have been survivable were actually incurring fatalities. In the course of their testing, they found that most of the deaths caused in what should have been survivable air crashes were not due to fire injuries as you might expect, but were in fact due to load injuries. A load injury occurs when a brief but extreme amount of force is exerted on the body. During testing, researchers discovered that passengers were experiencing the full force of the impact of the plane during a crash, producing enormous unsurvivable load forces on their bodies. This is very similar to crash data discovered by automobile makers. Car accidents of the past were much less survivable than crashes in recent years. This is because newer automobiles have been designed to absorb and dampen the majority of energy in a crash, keeping passengers safer. The researchers at IDRF began designing and implementing new dampening systems to be placed on board airplanes. New systems like energy-absorbing seats dissipate and absorb energy during a crash, greatly reducing the load weights being experienced by passengers. This single change has saved many lives.
We found that changing the seats has made a lot of difference and saved a lot of lives. However, there's more we can do. When you look at the whole system, like changing the structure so that not only do we have the seats stay attached, but energy is taken out of the system through the structure itself. And they're wearing special restraints that keep them in their seat, and also may even put airbag technology in some of the aircraft. And for large airplanes, we're even looking at changing the design so that it will deliberately brake in certain places. then we can determine where not to put hot things or sharp things or fuel lines and things like that so that people can get out or egress through these openings in the large aircraft.
Lisa, a lot of the things that you described are things that NASA and the industry are doing to make flying safer, but is there anything the general public can do to make flying safer?
Yes, you can check your luggage, all of it if possible, because things in the luggage bins do become flying objects in a crash event. Computers, for instance, are very heavy objects, and if they come flying through the aircraft at landing speeds of 200 knots, then you have an issue because it will definitely injure people. People are not replaceable, things are, so if you can check the luggage, then you're doing a great service to prevent injuries in an accident. We want people to walk away from these survivable events and not have any injuries. And we're working hard to get there.
The Impact Dynamics Research Facility was named a National Historic Landmark in 1985 to commemorate the work done there in lunar landing research. Coming up, we'll find out how an instrument used to test space shuttle tires is now being used by doctors to help patients who suffer from head trauma. But first, did you know the first person killed in an airplane accident was Lieutenant Thomas E. Selfridge? On September 17, 1908, airplane inventor Orville Wright took Lieutenant Selfridge up on a demonstration flight for the U.S. Army. During the flight, one of the propellers separated, causing Wright to lose control. The plane fell 75 feet to the ground, killing Lieutenant Selfridge, while Orville Wright suffered a broken leg and pelvis.
Unfortunately, head trauma is a fairly common injury encountered in critical care. Associated healthcare costs run over $7.5 billion in the United States alone. Brain injury is a major cause of long-term disability in the pediatric and adult population. When head trauma occurs, the cranium or skull expands due to an increase in pressure. The current method of monitoring this pressure requires mounting a device in a hole drilled in the patient's skull. Researchers at NASA have invented a non-invasive method for the measurement of intracranial pressure that uses ultrasonics. Derek Leonidov has more on this fascinating new invention.
Every year, nearly 400,000 people are treated for head injuries in the United States alone. In 50 to 75% of those cases, the pressure inside the skull rises to a degree that could be fatal. That is why keeping accurate measurements of cranial pressure is crucial. Unfortunately, the current methods of measuring pressure in the head involve inserting measurement tools like catheters or needles directly into the brain of the patient. Fortunately, NASA and its partners at the University of California, San Diego Medical School have developed a new device to monitor intracranial pressure that doesn't need to be inserted into the brain at all. This new device is useful not only, for example, to help head trauma cases, but is also being used by NASA to help astronauts combat space sickness. I spoke with Dr. Tom Yost at NASA's Langley Research Center to find out more.
We're actually using ultrasound to replace the older technology which required drilling a hole in the head in order to measure intracranial pressure. We think that this is a much superior way to avoid a lot of the problems that are associated with the measurement of intracranial pressure as it's now practiced in medicine. What we are trying to do is to use ultrasound as a means of measuring intracranial pressure. And the way we do it is we place a transducer, an ultrasonic transducer, on the side of the skull, and we send a wave through the skull, and that gives us the clues that we need to determine what the intracranial pressure changes are inside the skull. We really think that this technology that we've developed here is revolutionary in a sense, because we think it will mean that once adopted, that nobody will ever have to have a hole drilled in their head again to measure intracranial pressure. When one drills a hole in the head, you compromise the brain in a way that allows infection to go into it. And regardless of how careful the hospital or the physicians are, infections can indeed creep in and cause a brain infection, which is very, very difficult to try to solve.
When our body is injured, swelling is a natural and effective way to protect the injured area. Although when the brain is injured, it has no room to swell inside the skull. The pressure from the swelling can cause major body functions to shut down. This condition can cause the patient to lapse into a coma or could prove fatal. To measure the swelling, doctors usually drill or burr a hole in the patient's head and insert a needle or catheter into the ventricle region of the brain. This is highly invasive and can increase the risk of death due to infections. So how did NASA researchers get involved with something like this?
Well, we originally started to try to use ultrasound in a bolt tension monitor for use on the shuttle. It's very critical that we adjust those shuttle bolts very, very precisely for safety reasons. What we also then wanted to do was to use the same ultrasound ideas that we had developed for that in measuring intracranial pressure. Now it looks like that in this decade we are going to use it with the shuttle astronauts in order to check space adaptation sickness and some of the issues associated with it.
Currently, up to 40% of all astronauts develop a condition called space adaptation syndrome in their first few days in space. The symptoms of this syndrome can include nausea, vomiting, and increased swelling in the upper torsos and head of the astronaut. When an astronaut flies into the weightlessness of space, his body continues to function as if he's still on Earth, pushing fluids up, causing an unbalanced fluid distribution in his upper body. The condition can become very serious during a spaceflight when vomiting may impair the mission. This is where the intracranial pressure monitor comes in. The objective of this monitor is to assist in the prediction and treatment of space adaptation syndrome. Researchers will place a small monitor on the head of each astronaut, which will measure for increased intracranial pressure. Since each astronaut's body reacts differently to space, the instrument will help detect those astronauts who are more susceptible to the syndrome. Once researchers understand how the syndrome affects the individual, they can find different ways to treat and prevent it from occurring, effectively eliminating the problem from spaceflight.
Derek, while it is being used now for just a few people on shuttle, namely the astronauts, we hope to make this available for general medical use so that no one will ever have to have a hole drilled into their head to measure intracranial pressure again.
In the 1940s and 50s, the unofficial motto for flight researchers was higher and faster. And by the late 1950s, the last frontier of that goal was hypersonic flight to the edge of space. Reaching this challenging goal would require a huge leap in aeronautical technology, life support systems, and flight planning. Reacting to this goal, John V. Becker and his team at NASA Langley set out to meet this challenge. The resulting work led to the development of the revolutionary X-15 aircraft. This amazing aircraft not only went on to break speed and altitude records, but helped usher in the space age. By the mid-50s, research planes could fly at 3 times the speed of sound, but researchers knew that the technology existed to build an aircraft to fly at least 5 times the speed of sound while reaching altitudes that bordered the edge of space. This is where the idea for the X-15 was born. Although speed was important, it was not the only requirement.
The propulsion for propelling a manned airplane at hypersonic speeds was rapidly becoming available in the missile program. However, structural technology for high temperatures was practically non-existent. The aerodynamics was in its infancy, and it was fairly clear that putting what we knew together in an airplane that would go as far as possible toward hypersonic flight should be the real objective.
Researchers wanted to design a plane that could accomplish many different goals. They wanted to design a pure research plane. In early wind tunnel tests, researchers quickly saw that heating would be a problem for conventional metals. To combat this problem, researchers designed the X-15 structures primarily out of titanium and stainless steel, while the airframe was covered with Inconel X nickel. Inconel X was a new alloy that could withstand temperatures up to 1,200 degrees Fahrenheit. When flown at temperatures higher than 1,200 degrees, the plane was covered with a pink ablative material which would boil away, carrying the heat with it.
By using this technique of short immersion in the hypersonic environment, we were able to get in there and make our measurements and then decelerate before the structure got into trouble.
The X-15 was powered with a rocket engine that was capable of developing 57,000 pounds of thrust. This amount of power could